So the motivation behind this work is that today we're seeing malware becoming more and more complex and sophisticated. And to battle this, we need more sophisticated malware classification systems and techniques. So this is a continuation of the Cougar framework, which is previous work of ours. Cougar standing for Clustering of Unknown Malware Using Genetic Algorithm Routines. So we essentially employed a malware classification system using a genetic algorithm, which is used for parameter optimization. So we essentially feed Cougar a clustering algorithm, and it optimizes the parameters based on given objectives, which we'll get to in a minute. And we opted to go with static analysis rather than dynamic analysis. So we chose to use function imports from the Ember dataset in order to avoid time and computational overhead involved with dynamic analysis of malware. So like we mentioned, this is a continuation of our previous work involving Cougar. So what have we done? How have we extended this work? Well, we've extended it in 4 main ways. So the first one is we have included functionality for 2 new algorithms, and we've tested those. So those are HDB scan, which is hierarchical density-based spatial clustering of applications with noise, and expectation maximization. We've included a new scoring metric called cluster representation, and this is essentially a look into each cluster and looking at the degree to which the function imports for each malware sample are shared within that cluster. So it's essentially the degree of similarity between function imports in a cluster. We've scaled up the system from 2,000 samples up to 10,000 samples. And we've included a comparison to Mutant XS, which is a leading malware classifier from the literature. So a detailed literature review is included in our written paper, but here we just wanted to discuss Mutant XS a little bit further and analyze some of the techniques it employs. So firstly, it extracts data from each of its malware samples in the form of n-grams. Each of these n-grams are then turned into vectors. Once this data is vectorized, each of the vectors are hashed using the feature hashing technique to save space. And then a prototype-based clustering algorithm is employed. So a diverse set of prototypes are chosen from the data, and these prototypes are then clustered among themselves, and each non-prototype then falls into the cluster containing the prototype most similar to itself. So a detailed comparison is done between Mutant XS and Cougar later on in the presentation. This image provides a step-by-step analysis of how Cougar works. So first, function imports are taken from the Ember dataset and are stashed into a Apache Parquet table. These are then vectorized into bit vectors, where each bit represents the presence of a function in a malware sample. These are then handed to the reducer, which utilizes the UMAP algorithm to reduce data to 2 dimensions. And these are then passed to the Spark cluster. So Cougar is implemented using Spark for parallelization of the clustering. So the clustering happens here using the genetic algorithm, and then the results and the clustering scores are given to the security analyst from there. In our tests, we use HDB scan and expectation maximization, as were mentioned, and these are benchmarked against DB scan, which is the leading algorithm from our previous work with Cougar. So our clustering is employed using a genetic algorithm. We selected NSGA3, which is the 3rd edition of the non-dominated sorting genetic algorithm. The parameter selection for that algorithm can be seen in the table here. We chose 4 partitions, 100 generations, crossover and individual mutation probabilities of 1, and a gene mutation probability of 0.25. And we gave it 3 clustering objectives. So we first said it should maximize the amount of highly homogeneous clusters. It should maximize the median cluster size, and it should minimize the sum squared error. So more on these metrics can be seen in the written paper. For this work, we scale up to 10,000 malware samples. And here in this table, we can see the clustering results of our top 2 individuals for each clustering algorithm sorted by quality cluster count. We highlight DBScan and HDBScan here. And we use DBScan as a bit of a benchmark for our 2 new clustering algorithms that are being employed, as DBScan was one of the top performing algorithms in our previous work with Cougar. And as we can see here, dbScan continues to perform quite well. It actually beats HDBScan across the board in all metrics but median cluster size. And median cluster size is a metric of interest for us. As median cluster size increases, we do expect other metrics to fall, and we can see that happening here with HDBScan. Benchmarking now our top expectation maximization individual with our top dbScan individual. And the story is much the same as with HDBScan, except now to an even greater degree, as median cluster size for expectation maximization is way up at 24 versus 10 for dbScan. We again see that across the board, dbScan continues to outperform, as we would expect for such a difference in median cluster size. We like the variety of results we receive from each of these algorithms, and a security analyst may prefer larger clusters and be willing to take a hit on accuracy for convenience in certain situations. The multi-objective nature of our clustering framework is constantly attempting to balance these factors out. In this table, we've sorted our top individuals by cluster representation rather than by quality cluster count. So cluster representation is our new metric, and it records the degree of similarity of function imports in a cluster. So we've highlighted our top dbScan individual here, which has achieved a perfect cluster representation of 100. This goes along with a weighted F1 score, a homogeneity, a completeness, and a V-measure considerably higher than our top individual by quality cluster count. It maintains this along with a low sum squared error and a respectable 185 quality cluster count. These results demonstrate the validity of cluster representation as an effective metric. We wanted to compare Cougar to a leading malware classifier from the literature. For this, we chose Mutant XS. We created an adaptation of Mutant XS in Python based on the algorithms laid out by the authors. In order to facilitate a direct comparison, we used the same Ember data on our Mutant XS trials as we did on our Cougar trials. We first implement Mutant XS using the suggested parameters from the authors. This leads to disappointing results. These can be seen in the highlighted row. After some manual tuning of Mutant XS, we managed to achieve the results displayed in row 2 labeled top Mutant XS. Though these results are good, they still fall short of Cougar's top individual by cluster representation, shown in row 4. Another piece to highlight here is that the top Mutant XS results were achieved after manual tuning, whereas parameter tuning is built into the Cougar framework. To conclude, dbScan continues to perform well, scoring highest in most of our metrics. Expectation maximization and HDBScan, however, did manage comparable results, but with higher median cluster sizes. This provides Cougar with some flexibility, as one may be willing to sacrifice some accuracy for larger cluster sizes, depending on the situation. Our top dbScan individual outperformed the top Mutant XS individual by 10 to 20% on our metrics. And this top dbScan individual happened to be sorted by signature representation, demonstrating the validity of our new metric. In the future, we will look to further increase scalability, analyze and look to minimize computational costs, and broaden our feature scope beyond function imports from the Ember dataset. We'd like to say a special thank you to NSERC, IEEE's Computational Intelligence Society, Dalhousie University, and the NIMS Lab for making this work possible.